Dr. Shoemaker, thank you so much for coming on.
No problem.
How are you doing today?
I'm okay. How are you?
I'm pretty good.
Yeah, it's nice out. You can't tell in here.
It is warming up, but all the pollen's coming out. And I saw it was like raining like sheets of pollen the other day. It was...
In Atlanta, the cars would turn green.
Oh, really?
There's so much pollen.
Jeez.
Yeah, worse than here.
Yeah. Worse than here, that's...
Not for allergies, just the sheer pollen.
Oh, okay, yeah. So, getting started, I think it's important to ask you some definitions first, just so that everyone is on the same page about what we're referring to. Okay. So, could you describe to me what is a black hole?
I guess so. You have your handy-dandy equation up there. There's a lot of different ways to describe a black hole. One way is to say it's a collapsed star that's collapsed all the way in on itself to the point where everything, all that matter that was there is now at a singular point. And we call that a singularity.
Yeah.
Another way is to say it's a region of space that light can't escape from, thus a black hole. We would describe it as a place of infinite curvature endowed with an event horizon in general relativity. Just depends who you are, where you come from. And we would write its equation like the one you have on the board.
Would it be
Yeah,
this one?
This guy? That guy?
Yeah, the Schwarzschild? Yeah.
Just for Schwarzschild, just if it's not spinning.
Okay.
It's static.
And then what are coupled black holes?
So this solution that you have here is the simplest you can write down for a black hole because it's not spinning and it's static and it just sits there. It's also the solution to the external geometry of a non-spinning star, just not the matter part. But we often have stars that are formed as two in a binary pair, and they're orbitally bound. They bound together. So if both of those become a black hole through their evolution, that would be an example of two black holes that are orbiting each other and doomed to merge because general relativity tells us that the black holes in a binary pair like that emit gravitational radiation, so they're always losing energy. They're converting the energy in their orbit to gravitational radiation, so the orbit shrinks and they eventually merge together into a single black hole.
What exactly do you mean by gravitational radiation? I've never heard that.
Yeah, it was detected for the first time in 2015 by an experiment called the LIGO experiment, which I am part of. And so what gravitational waves are, they're kind of like, they play the same role that electromagnetic waves play, right? So like electrons move, photons, are excited. We see photons. Our eyes are built to detect electromagnetic radiation. Yeah. So that's how we see the universe, right? All these telescopes take these beautiful pictures. Electromagnetic radiation happens because a mass accelerates in a non-uniform way. So we can make it, but we will not detect that. It's too small. So, but when two black holes merge, that's sort of the biggest, baddest form of gravitational wave, like how you can produce the strongest gravitational radiation, and that's what we detect here on Earth, is the echoes. It's almost more like a vibration in space and time, and that we pick up that vibration. Like if you banged to this table and felt that vibration coming, the gravitational waves propagate through space and time, disturbing it, and we measure that disturbance.
Yeah, I want to go back to a little later in the conversation. I do want to ask you about kind of propagation of gravity waves. It seems like you can use gravitational radiation and gravitational waves sort of interchangeably.
Gravity waves is the restoring force, so that would be like ocean waves.
Okay.
Gravitational waves are different.
Gravitational and gravity waves are different.
Different.
Okay,
we use the word gravity waves to mean something else in physics.
Okay.
We mean that to be like what you might have done in a waves class. We would talk about the restoring force. So what is bringing a wave back to its equilibrium position?
Yeah.
That would be gravity. For an example, like an ocean wave. Gravitational waves move. They travel at the speed of light.
Yeah.
They don't interfere very strongly with matter, so they're just different. It's just if you Google it, it gets very confusing because people use the word gravity because it's easier than gravitational, but gravity wave actually means something specific to so that it can be confusing.
Yeah. Okay. Gotcha.
But we can decide gravity waves mean gravitational waves. I don't have to be nitpicky.
No, let's use gravitational
It's
waves
just
if
that
that makes more sense.
Like
yeah.
if people, there's a guy in the hallway, so I waved to him because that's what I do. He's like, who's this crazy lady? Anyway.
Okay, yeah, that seems to be a common theme in physics is like variables that are almost exactly the same, but they mean two very different things. Depends on the context.
We just don't have enough language to cover.
Yeah.
All, especially variables. Yeah, they're a mess.
Okay, so back to what I said I wanted to cover in the future. Why do gravitational waves propagate through space instead of just creating gravity at some local position, right?
I mean, you could do that. You could
Yeah.
You could be some kind of mad scientist and produce. I mean, you couldn't. None of us can. None of us know how to do this. But you could imagine gravitational waves interacting and collapsing. That's not insane. That's part of the theory. But the way gravitational waves propagate is that, once you cause them, once a mass is disturbed space and time and generates gravitational radiation, then just like light, it's going to propagate until something stops it, right? It's not like light stops and pools somewhere. It travels until it hits this table, so it's dark under the table because the light has interacted with the matter in the table. Gravitational waves would go pretty much straight through, but that's just because the way they interact with matter and energy is just weaker. So it's the same thing, like I can defy gravity by lifting up this phone, right? Because that interaction is a weak interaction at this level. It's a very strong interaction at cosmological scales, at a black hole scale, if you're in the vicinity of two black holes. But it's very easy to defy gravity. So it doesn't interact with like little matter, like what's in the strong nuclear forces that are holding this together in the same way light does.
Yeah, and it's kind of mind-boggling for me to try to wrap my head around the fact that in normal waves, so if I hit the table, right, and that wave travels through the table and I can hear the acoustic wave in my ears, it's distorting the molecules through space, but time remains constant. But with a gravity wave, you're distorting space and time, right?
Yeah, it's definitely, it's like the reason why I think nowadays we consider quantum mechanics and general relativity to be the two subjects that are kind of the most mysterious and interesting to learn, because they violate our intuition. Our intuition is built from our daily lives here. And while quantum mechanics and general relativity are very important for the working of your phone, it would not work without it. We don't experience it on a daily level. So we make these analogies, and it's dangerous because there's a limit where it's not correct, like what I'll say. When I try to explain a gravitational wave, I'll begin to use language that's imprecise at some level, and then we start to get in trouble.
Yeah, you start to get into this realm of like you just cannot, for the life of you, conceptualize like really what is happening. You have to like for the example of having like a sheet, like a bed sheet as space-time, and then you have different weighted balls that are distorting the sheet in different ways. Like, it's a good analogy, but it's not super accurate.
No, I've met people, I don't blame them, in the public who always have heard of that rubber sheet analogy and then don't understand that you could orbit a black hole because they're thinking of it as this like funnel in space, So that's because it's an embedding diagram. We only understand curvature by seeing it in 3D and watching the 2D curvature. So we embed everything in it. It's just natural the way we think, but not accurate. But that's okay. That's why we have all the math to help us, because then we can communicate about it correctly. But words are hard. So I will fail you. I'm sorry. But gravitational waves have been detected. So. And they were predicted by Einstein's equations of general relativity, and it matches so far.
Yeah.
So it's always amazes me that our brains could think of these things and then actually build a detector capable of measuring it. It's kind of wild.
Yeah, it is wild. And it's all through just like mathematics and really, really smart people thinking for a really long time about really crazy stuff.
Lots of people. Some of them probably weren't even that smart, but lots of people.
Yeah.
It's amazing to me. So that part's really cool.
Yeah, when you mentioned people thinking that black holes were just these cosmic vacuums, you were referring to me
Well,
before I did my research. It was kind of also mind-boggling to me that, like, you can orbit a black hole. Like, if we replaced our sun with a black hole, the orbit of our planet wouldn't change that much. Yeah.
Yeah, it's the same geometry outside. The black holes describe the same geometry as outside of our sun. Mm-hmm. It's just the sun would be tiny now. The black hole would be pretty small. Okay. You'd have to get a small enough radius to make the sun a black hole. It's not massive enough to form a black hole. We'd have to smush it down to a pretty small. I think it's like a golf ball.
Yeah, it's something. Really,
but yeah, we
really,
would die
really
from
small.
lack of light, but not from the black hole. It would not suck us up. Don't pass the horizon, but you would be destroyed by so if we did have a small black hole, we would be destroyed by tidal forces before entering the horizon, depending on the size of the black hole. Just by like the difference between the tide at your feet and your head if you fell. Where if you're in a giant black hole, you could pass the horizon and never feel it.
Whoa.
Right? Because the tidal forces are different than that calculation is very different than if you're just doing a escape velocity of light from the black hole. So there's fun things.
If you were in the horizon,
I picture this.
And you were
swimming.
in a huge, it's not bad, in a huge, like, supermassive black hole, like you said, and you pass through the horizon, if you were to look out to the universe, could you see all that light coming in?
So you do see, this would be true if you were accurate enough in your measurement. Anytime you'd fall deeper into gravitational potential and look up, you'd see everything blue shifted. Just like when we look high in a gravitational potential, we see things red shifted. Mm-hmm. We're used to that point of view because we're taking a spectrum of stars, and so we see things red shifted. But you would see it blue shifted as you fall. You don't even have to fall into the horizon. It's just that you start to see the most interesting effects as you get closer.
Yeah. And then as you would get closer, eventually you're going to spaghettify.
Well, depending on, like, if, gargantuan. It really depends on the how big the black hole is, its mass, where that spaghettification would take place. But it is interesting. There's something else that's fun about. Oh yeah, because the part of the problem is that black holes will grow. So if you put your hand in, you're kind of doomed because now the black hole is like growing in anticipation of the added mass.
Yeah.
So yeah, you don't want to get close. It's fun to play with people's minds and say we could be in a black hole right now and not know it, because the definition of an event horizon is such a bad definition, because it means that at the end of time and space, you could trace back the photons that made it out and the photons that don't escape to infinity. And then, so if the universe were different than we believe it was, if it were actually going to end in a collapse and a giant crunch, then a big black hole would form, and we would already, we could already know that. Now, we couldn't know it now, but in the end of time, we could have already been in a horizon, because we would be doomed to be inside of a black hole and not know it. So the event horizon is not the most useful definition of a black hole.
Yeah, I love physics. I love thinking about stuff like
it
this.
Is fun. Yeah. That's why my favorite class to teach is the undergrad relativity, because the grad one, you have to go so far in the math, you don't have time to play. But the undergrad one, I like to play.
Do you find your students just like you're explaining an analogy like that, and they're just kind of like slowly, their mind is being blown?
Sometimes they ping and like they get something, and that's really fun because you can watch. You can see them like, oh wait, I think I get it now, because it's a lot to unpack, so it takes time.
So when you say that the event horizon is a bad definition, it reminded me of a question I wanted to ask you about. So there's the event horizon, and then there's the apparent horizon. There we go.
Yeah.
Apparent horizon. What's the difference between those two?
So the apparent horizon definition doesn't have the mathematical rigor that the event horizon has, but the apparent horizon, if it exists, because they're not guaranteed to exist, that's the problem. Depends on your coordinates, all sorts of other mathematical things. But if it exists, it will be either the same as the event horizon or inside of it. And it's a nice definition for me, because I solve Einstein's equations for black holes on a computer, so I need to know where that singularity is. Where's the black hole on a slice of space? So if you imagine you take all of space-time and you do it in chunks of 3D space so that the movie runs up in time, each one of those slices of 3D space I can use the divergence of basically light rays, or we can call it that. And when they're neither converging or diverging, then I can define a surface that's trapped. It's not expanding or contracting, and it happens to coincide with an apparent horizon. So you'll find these interesting surfaces that are just sort of surfaces of no expansion. Because you can imagine if you shined a flashlight, the light goes out, it expands. So you take a piece of paper further and further from that flashlight, the circle the light intersects with the piece of paper looks bigger and bigger the further away you go from the flashlight. So this would be light that doesn't do that. It would stay, it wouldn't get smaller or wider, and that would be a signal with other things, I'm simplifying it, that you have an apparent horizon. So I can find it on any slice of space and then use it to say my singularity is in there.
Okay.
Beware. You don't want to step on a singularity because it's infinite.
Yeah.
Codes don't like that. They just don't like infinities. So we have to be careful.
Yeah, let me take a second to
I could draw it if you
sponge
wanted.
that in my brain. Yeah, if you want to draw it,
Chalk, am I
chalk
allowed
over
to
there. Yeah, for sure.
There's even chalk in this place. Okay. We'll draw it real tiny. Is this going to help? Let's see.
Yeah, I can erase some of this if
That
it's not
DET,
useful.
that you can erase that DET. We don't, I'm not sure what it is. Wait, don't say that out loud. What is that? I'm kidding. Okay. Sorry, microphone. Okay, that's R, so it's going to be spatial.
Yep.
This is time.
Okay.
So we're going to plot space and time. We're going to ignore the other two spatial dimensions.
Okay, so for people that are audio only, she put R in the x-axis and time in the y-axis, and it just looks like a normal graph.
It does look like, except you expect it to be XY instead of RT. And so R is horizontal, time is running up the vertical axis. Now imagine a star that's spherically symmetric collapses. So we only need R. And in time, if you think about what happens, the radius shrinks in time. So we'll draw it. We're going to draw a line of shrinking R in time. So eventually, the surface of the star goes to 0 when we form a black hole. So there's a singularity in here. We draw singularities in the business as squiggly lines, very technical. Just kidding, it's not. The event horizon will start to form in anticipation of that singularity. So at some earlier time, the event horizon forms. And I'm drawing something that looks like a parabola, but it's flat outside. It's a straight vertical line outside the surface of the collapsed star.
Yeah.
That's my event horizon if nothing else happens. And I could find it by saying, will a photon inside this star that's collapsing escape to infinity? Like some friendly guy out here who's got a telescope and he's looking at this light. Light outside the horizon will make it, but light inside won't, which is why this little bit of star is doomed to be inside because it's not going to make it out. So that's how we know. Now let a shell of matter, spherically symmetric, fall later. So you had some matter that was outside the star and it collapsed at a later time. So the event horizon is going to anticipate that and form like this. This is the true event horizon. So what I drew was another surface that looks again like a bit like a parabola, but outside, now that more matter came in. So now even this bit of light that we thought was safe won't make it because it got focused later by this extra matter coming in. And so
Okay.
I didn't draw this.
Starting to get it now.
I know, it's tricky. No one ever said this stuff was easy. This thing right here that looked like it was the horizon initially is the apparent horizon. Okay. So in that moment of time, every R slice of that space, there would be a special region in the space that would look like it was not expanding or contracting. That would be my apparent horizon. And it would lie inside the true event horizon, so I would be safe using it. I wouldn't be 100% accurate, but my singularity is contained inside the region I think it is. So for my purposes, I'm perfectly happy with this.
Gotcha. So I'm a huge star. I start collapsing in on myself. And as I'm collapsing in, and I get denser and denser and denser, there becomes a point where I start forming that event horizon that a black hole has.
And you can't see it. It's not like there's a black shadow. No, right? It's purely about a boundary between photons that in principle will see their light far away if we had a telescope, and photons that will never see their light.
Okay. So I'm starting to form this event horizon that you can't see. And then as I start to form this, now all this extra matter comes in. So now that light that you thought could escape doesn't. And so you form another event horizon.
The true event horizon.
The true event horizon outside of that. And then the intersection between your two mass curves or your two radius curves, as they go up, that intersection with your y-axis, your time, tells you...
This is the
No.
Yeah, it's this guy.
It's that guy.
Yeah.
Okay, so it's the intersection between the event horizon and your mass curves.
Yeah, because what I'm drawing here is weird, right? These are imagining if I had to, I want to call them null generators so badly. Trying to think of language I could use instead of that. But it's like the flashlight again, kind of. So it's like these are trying to trace out what a flashlight would be doing. And here it looks like it's still expanding, so you think you're safe, but that matter is going to refocus it, so that light is actually going to contract down. Where here it looks like, oh, it's neither expanding or contracting. I'm in a special spot. I must be at the horizon right there. Because light here is going to contract. Light outside it is going to expand.
Yep.
So it seems like it's special, and that's what we use for the apparent horizon.
Ah, gotcha. So the expansion of light outside of that, like the entire collapsing star phenomena, is balancing out with the contraction of light within.
Kind of. I mean, I'm using an analogy.
Okay.
But you can think of it. You can think of it like how would light be behaving in the vicinity of that, what's happening, and so we can have this local definition by thinking about the contraction and expansion.
And there's, from what I understand, like once you have a black hole, the event horizon is pretty homogeneous and pretty stable, but your apparent horizon, there's more heterogeneity, or it's like defined in, like you said, like those certain grids in space.
It looks perfectly normal on every spatial slice. It could grow. So if more matter falls in, I have to recalculate later. So it doesn't have to be beautifully smooth and pretty like an event horizon will be. Yeah, it could discontinuously change from slice to slice in that sense.
Okay. And then going to the concept of mass in a black hole, how, like, do black holes have mass in the same way that you and I have mass? Or is it something a little bit different?
I think it's really the failure of the theory.
Yeah.
Because we take all this mass and we scrunch it down into a single point and we go, oh, well, it's infinite now. I don't know what it is. I lose all my physical laws. So there it is. And then the weird thing also is that I could describe the geometry of a black hole by never even using matter. I can't tell you how I formed the black hole, but I could perfectly happily and do for a living describe black holes without even bothering to collapse matter. I just have an infinite point in the center, and then I can talk about the geometry of a black hole. So it's a perfectly viable solution to a vacuum spacetime, but you just don't know how it formed. Yeah. So that's what makes it so hard, because there's no... This gets into the realm of the physics that is super exciting, but, what is it? People are trying to figure out this inconsistency, like the famous fact that we don't have a quantum theory of gravity, because we don't have a way to explain what's happening in a really small scale.
Yeah. Yeah, from what I was reading, that is the proposed kind of new development of, like, how are we going to understand this? Let's try and use quantum gravity to understand what's happening at that infinitesimally small.
Yeah, because you're always looking for ways that physics is flawed to get the next, because it should be. There's always a limit to our understanding. That's an obvious one, because we know that doesn't, we can't marry quantum mechanics and general relativity successfully. So, the funny thing is that so far, astrophysical black holes, that our ability to detect them have been consistent with this picture of general relativity. We're in the early days. We've only been at it since 2015. Detectors keep getting better, but so far everything's consistent with, all the general relativity predictions.
Yeah.
Which would mean that the black hole, what we're really trying to do is prove that some of us, astronomers probably disagree, but the black hole is really described by Einstein's equations. It would mean that it's only described by 2 or 3 parameters at the end of the day. It's a very simple, and we have a very clear way how that behavior is, how it manifests on the gravitational radiation. So we're trying to get good enough to test it.
And those 3 parameters are mass, charge, and
The spin,
angular momentum.
Mm-hmm.
Yep.
And charge we usually ignore because the universe tends to make neutral black holes.
Okay. Yeah. I was reading about that too. So as soon as you like create a charge in the black hole, there's a charge in the universe that balances it out.
So
Yeah.
We still will pay attention, right? Because that'd be fun to see if it wasn't true. Of course we're gonna try everything. That's what theorists do. But that's sort of like one of the big, exciting things because we're getting closer to the time we'll be accurate enough to be able to see that if that expectation is being held out.
Okay. So you'll be able to detect with the instruments that you have if the black hole has charge or not.
Or if it has the charge would be cool, but we actually want to see that. So Einstein's theory very clearly describes the radiation emitted from a black hole that's been perturbed. If it's, that it has only mass, spin, and charge. Like we know exactly what that radiation should look like. So if we detect radiation that violates that, that would mean it's not described by Einstein. And that would be super exciting.
Mm-hmm. So what other form of radiation could it give, or like would violate that?
So we're still expecting that from gravitational radiation.
Okay.
That's what we're using to find it. Because you can't really, these, at that point, it typically is after 2 black holes have merged, there isn't necessarily any matter around it. So you're not seeing electromagnetic radiation. So you're really purely looking at these things with gravitational waves.
Gotcha. And when you say angular momentum of a black hole, are black holes kind of spinning like our sun does? Mm-hmm. And do they develop that spin? Or when do they develop that spin in their life cycle?
Yeah, it's a good question, right? That's one of the things people want to know. You could imagine that the star was spinning that collapsed into a black hole and it inherited its spin. You can imagine 2 black holes collided and the merged black hole that comes to the end got a new spin because of that interaction. That's the types of things. Or you can imagine that there's matter accreting around a really big black hole in the center of a galaxy, and that accretion, impacts the spin of the black hole one way or the other, increasing it, decreasing it, what have you.
So how do you spin something that is infinitesimally small?
Well, it's inheriting it from its origins. Oh, how do you, if you have 2 black holes and they merge, how do I spin it?
Well, so you have a star that's spinning, and then it collapses into...
So it kept it. So the space-time kept it. The geometry itself was spinning.
Oh, okay.
Right? So the description of a spinning black hole, there's a region outside the horizon called an ergosphere, which is frame dragged. Like things are actually, the space-time geometry itself has an angular momentum, which is fun too.
That's really, really cool.
And it's really kind of crazy.
Yeah.
So when I study 2 on a computer, because you can't solve them on a piece of paper. You asked it before. I don't even know if I ever finished it, because I said that's the solution of the geometry of a single black hole. Our problem is it's a nonlinear theory, so we can't just add 2 together and have a solution for 2. We have to solve Einstein's equations for it.
Yeah.
So
Which
that's what we do.
This big one
Yeah.
right here. Yeah.
You have a cosmological constant and everything. G mu nu. I just set that equal to 0, believe it or not, and it's still hard to solve for 2 black holes in their final merger at Buck.
Yeah.
But we used TAC, obviously, because we're lucky to have our own supercomputer. So that's what and then one of the solutions to this equation on the board is the dynamics of what the black holes are doing, the geometry, all this crazy swirly stuff, and the gravitational waves that LIGO detects.
So when you're spinning this black hole, it's like, I don't want to say shearing, but kind of like bending space-time.
I mean, people think of it as, I call it frame dragging. You can think about it, what's happening when you have a water current. It's not the same, but you imagine things getting caught up and going with the flow. I mean, it is similar to that. It's just more complicated. But
Okay.
it's not a crazy way to think about it.
And from those really awesome little videos I saw of black holes converging, they do that same thing, but now they're spinning. They're not so much rotating in one spot. They're like spinning around each other.
Yeah, they have.
Right.
So there's many, just like in Newtonian mechanics, you have orbital You have a total angular momentum that's the sum of any spin about the axis plus the spin about each other, or the angular momentum about each other. And so when we do the black holes, just like any other problem, an angular momentum problem, the angular momentum of each one, the angular momentum of the orbit, and then at the end we'll have a final black hole that also spins. And so there's almost like a simple equation about how that happens. And so we radiate angular momentum because we'll probably have an excess.
Yeah.
So that's part of the radiation. It's angular momentum and mass.
That's super cool.
Yeah, that's fun stuff. But a lot of it you can study
Yeah.
without black holes.
Mm-hmm. So you would take, let's say you were modeling this. You take your model and you would say, this is how fast this black hole's spinning. This is how fast this one's spinning. Here's the mass of this one. Here's the mass of this one. And then I guess we're not super worried about charge.
No.
At the moment, yeah. And you would say, like, and then from that you would predict this is how they're going to move in space.
We would, depending on how close they are, that would be their orbital speed.
Yeah.
And then we could predict, well, we couldn't until we had solved it. But now that we've solved it, we can tell you how many, if I started here, if I started at a certain separation, how many orbits would happen before they merge together. And that depends on what their spins look like. If everything's aligned, because one of the things we haven't talked about is that there's a limit to the spin of a black hole, according to Einstein's theory. So you could have too much angular momentum in the system that you would form a black hole at the end of the day that would violate that spin limit. But we see that doesn't happen. We radiate extra. We orbit longer to get rid of it.
Okay.
We were kind of hoping we'd see something crazy, but... And when I say see there, I mean in the theoretical predictions we produce on a computer. Yeah. So,
are you seeing it not break your rules because the overarching equation you're using, like, if you break the rules, it's violated, so the model kind of stays within, or is the model set up to where if it breaks, then it's going to tell you if it breaks?
So what happened was that most intuition was built from, because there wasn't a solution to the full equation, so people would take limits. I'm going to assume that things are far apart and small. What's the limit? This limit I'm talking about came from taking a single black hole and perturbing it. So there was no reason to believe that the full theory had to obey that limit, because we were solving it in its full nonlinear glory.
Okay.
So we really just did not know what the equations would tell us. And they told us that I'm going to radiate it all the way so I don't form some crazy spinning beast at the end of the day.
What's the limit of that spin?
We call it 1. We normalize it so that it's the angular momentum per mass. And it just has a certain ratio that gets respected in the single black hole limit.
So if you have a super huge black hole, then its angular momentum has to be smaller than if the mass is smaller?
Oof. I guess that might be true. Actually, it's J over M squared. We like it to be unitless, so we can call it from 0 to 1. So we just really say almost like a percent of maximal, how 100% is its maximal spin. But it's not like a neutron star, like a physical star is less spin, you can imagine, because it also has the physical bounds of like when will things break apart.
Yeah.
Where a black hole doesn't have that. Yeah, I'm not really sure I have a good understanding or analogy for the thinking of the scale up of a black hole in mass. Like it does go J over M squared, angular momentum over the mass squared. So I guess there is this relationship, but I haven't actually played with it. It's a good idea.
And then another question I had, and something that is also hard to wrap my mind around, is that how do you what is happening when two black holes merge? Are those two singularities becoming one, or is something really weird, or like do we not know?
We kind of know, we kind of don't. So another fun thing is that the singularity is being a single point is for Schwarzschild black hole, one that's not spinning. And the ones that spin, the theory predicts it's a ring. It's like a little singular. Yeah.
Oh,
it gets
that's
wild.
cool.
It gets really wild. We don't really have a perfect picture of what happens inside that, because we have to make a decision about when we solve these equations, we're solving them on computers. Now, so we can't actually have a singularity. So we do one of two things. We either remove the region and use boundary conditions, because a black hole, everything goes out, nothing goes in. So we use those boundary conditions, or we use a clever coordinate condition that kind of like sends the problem infinitely far away so we can ignore it. So we don't really resolve the region of the singularity itself to see how it behaves. We can do things like those trap surfaces we were talking about to get a sense for it, but it's unclear exactly what happened. And then at the end of the day, you probably have that ring singularity again. But the really, truly dynamic region, I think it's hard to say what's really happening.
And for my intuition, it seems like it would be hard to try and conceptualize something evolving through stages when time itself is distorted
hard.
So much.
Yeah, it's very strange.
Yeah, how can something evolve from one iteration to another through some linear
it's not
form
linear.
Of time? Yeah.
So we actually have partial differential equations that we solve to understand how we slice in time and space. Because part of the problem with these equations is that when you do an electromagnetic problem, you would have your geometry. People often think of it as a giant Cartesian cube, and things play out on top of it. We have to solve for the geometry at the same time as the dynamics.
Yeah.
So we're solving for what this geometry of the space-time looks like at every step too. Yeah. So it's definitely a tricky business, and it happens pretty quickly. So it's not like, the really truly dynamic part is fast too. So it's hard to, but people do it. In fact, we should probably spend more time slowing everything down and really trying to resolve deeply. We did one thing where we did that. We tried to resolve really deeply what was happening near the singularities, but we used the clever trick to send things far away to kind of ignore singularities. So we just kept finding more and more trap surfaces, like just echoes of them. So I'm not sure if I walked away with a deep understanding of what was happening.
You said trapped surfaces?
Yeah, these like special regions where aren't converging or contracting.
Oh, okay.
We would see them embedded inside each other, like just regions of them. Like one would be out here, and then inside there'd be another, inside would be another. So it was hard to say because you're trying to use them to predict where the singularity is, and you see them like say you had two black holes, and then at some point they merge into a single one. Right before they merge, their horizon looks like a peanut. Their apparent horizon looks like a peanut. Mm-hmm. But if you start zooming in to see what those singularities are, you'll start seeing more trap surfaces. So it just like circles around the singularity. Mm. And as they get closer and closer together, the more we resolve, it seems like there's always these trap surfaces around there. So eventually we run out of computer time.
So if I was Matthew McConaughey, driving a spaceship into a black hole.
Good luck. He'd be done.
I'd probably not be able to travel back in time.
No, probably not.
Yeah.
Yeah, it was nice though.
It was a cool scene.
Yeah, but that was, in fact, a lot of that movie was correct. Mm-hmm. I mean, from my point of view. But matter's the thing that ruins all that for us. Yeah. We don't know how. Matter behaves in a certain way as far as we understand it. So if I want to build my warp drive, I want to keep a wormhole stable, I have to violate our understanding of matter. Yeah. It's not really the general relativity that trips us up there. It's the thermodynamics and our understanding of energy and matter.
Mm-hmm. Like you can't send, are you trying to say that you can't send energy that is now somewhere back in the past because you'd be like adding extra energy to a universe that has a finite amount of energy?
It's like the warp drive, our Star Trek to get around. I can write down the geometry of a warp drive, and you can do it in such a way that you don't even violate the speed of light. Mm-hmm. But to build it, you would need matter that doesn't obey thermodynamics. Like the way it's pressure, it would have to behave in ways that we have all of our laws say can't happen. Yeah. Or it's like general relativity has no problem with a wormhole if you want to get to Gargantuan. But to make it and keep it stable, you would need to violate every known law of how matter behaves.
So like as soon as it would form, it would just disappear.
It'd be like, So as far as we understand matter today, it's just we just can't form those things.
Reminds me of quantum mechanics, where like as soon as you I can never reach my entire hand through this table with like
Oh,
some
right.
kind of quantum tunneling.
Right. The first time you learn about quantum tunneling,
Yeah.
so cool, I can go through the wall. Oh, all of them at the same time is tricky.
Or the charge of black holes. Like as soon as it's charged, the black hole's charged anyway, the universe balances it out and it's immediately gone.
It's tough.
Mm-hmm.
Yeah, there's a lot of things that could be true that we're not accurate enough to know yet. Just like there was no way Newton could have known all this stuff because he had no measurement that would be able to know. You gotta see.
There was no LIGO or.
Yeah. It took a long time for that. Tough one.
So I remember I was talking to you about, or in office hours, if you were far away enough from a black hole to where you're not going to get, spaghettified or anything, or you're at one of these supermassive black holes to where you're not going to immediately get stretched out.
And we have one in the center of our galaxy. We're in a nice, safe distance.
Okay. So say we're in the center of the galaxy. Right?
Okay.
And for whatever reason, black hole in the center of our galaxy is perturbed and produces this gravity wave. What would I feel if I was just kind of floating in space?
What would you feel? This is a question people have been asking me recently, and I'm having doubt and pain that I actually know the answer. Because we do this, I don't know who made this visualization for LIGO, but at the first event, there was a great visualization of the Earth, and the gravitational wave hits it, and it bobbles like a bowl of jelly. So we know that when the gravitational wave hits, it stretches, so it would be like if you imagine yourself standing with your arms out, your arms would elongate and shrink. And there'd also be a cross polarization so that you would stretch and squeeze along that as well, along the X and the plus sign. So those are the two polarizations of gravitational waves. So that's what is happening. But how would you I think by the time I would put you in a position where you'd feel it, you would have been tidally disrupted. Like I haven't done the calculation, like do you actually feel any of that? I'm not 100% sure. But it's a fun thing to think about, but I'm not convinced.
I mean, the wave moves so fast that there's no way your brain could react to what happened, right?
But it's not that it's a single, right? It's a long trail.
Okay.
So by the time it reached Earth, it was only sensitive in the frequency band of the detectors for 0.2 seconds. But that's because of the frequency band we were sensitive to. So it lasted for much longer. It's just that we caught, we saw that little peak. But yeah, it's an interesting fact. The reason why I hesitate is because when you talk about a gravitational wave hitting, you only need two masses to describe it. That's why LIGO's got two long arms that are perpendicular to each other, because that's the minimum amount you need to detect the stretching and squeezing. But if I laid a ruler down, that ruler would also stretch and squeeze. So we wouldn't be able to, we don't look at LIGO and see it move.
Yeah.
We use light's path because light moves at a constant speed and it has certain phase shift, and so it will accumulate. When it travels a path that's longer, we can use the fact that the speed of light is constant and understanding its phase to make a detection. So that's how we use it. So I'm just like, would we actually feel it?
I don't know if we would.
And I feel like I should know this answer. So I know there's people out there who do. So whoever you are, you can send me an email and tell me. But it has to be one of my colleagues or I won't believe it.
Because the space, like all the space around you is getting stretched too.
Yes, exactly. So tidal forces are different. That's almost like a Newtonian calculation that I can do. Where this isn't. So that's where I have my doubt and pain that, But if it were stretching, if it's stretching and squeezing big enough, I feel like eventually I'd have to break matter. There would be a limit. So I do think eventually it will, if I could do it strong enough. Like if you were close to those two black holes merging, you'd be in deep trouble. I'm just not sure what would get you first. The tidal forces from what's happening. Because gravitational waves do carry energy, so there's something very physical happening. So at some point you have to be impacted. I just don't know when. It's kind of a fun thing, but
you're gonna die, but
how? I'm not 100% certain.
Okay, I'm starting to get to intuition between gravitational. Now that you explain it more, gravitational and gravity waves. Gravity waves would be something more tidal, and gravitational is our space-time is. It's less like gravity traveling through space-time, and it's space-time itself is the medium
Yes,
that's getting distorted,
exactly.
that's moving more space-time.
And it's very firm, and that's why you don't, it's more like a vibration on a table where you don't see the vibration, but you could feel it if you had the right instrument than other things. So that's what makes it really hard. I mean, if that weren't true, our universe would be in trouble, right? We need gravity behaving like this so that we can lift things off the surface of the earth than this, but it took us a while to detect it.
So why does the polarization of gravitational waves differ from waves that we observe right now, like electromagnetic waves?
They're really, really similar to electromagnetic waves in a lot of dimensions, but theoretically, they're a different field. They have more, how do I say it? I want to use lots of jargon right now, which might mean I don't understand it fully, completely. It's some kind of gut instinct. It's a spin-2 field. It has different behavior it's still transverse and longitudinal. So when you study, I could almost do the similar thing to electromagnetic field that you'd be used to do the radiation, but those are always at 90 degrees, and it's just that ours are 45. So it's just a slightly different equation, really, that's causing its generation. But I don't have a really nice intuition to explain that simply without resorting to a lot of mathematical jargon.
So why don't we start with what a spin-2 field is?
That's the thing. I don't think I can tell you without
okay.
it. I don't have some simple thing like I have with all this other stuff.
Yeah, no problem.
Yeah, it's sad, but it's true.
It's a good thing for the listeners to read and myself to read.
You probably, the people who immerse themselves in that would be like a quantum field theorist, right? Where I immerse myself more in the equations are there, I'm solving them, I'm learning about them, but I'm not trying to invent a new equation. So I ignore a lot of the deeper math that you needed to arrive at the field equation.
I'm going to confirm these equations instead of I'm going to just totally create something new. Yeah. So how do we tell the difference between gravity waves generated from, let's say, 2 neutron stars colliding as opposed to 2 black holes, or maybe a black hole that's like a singular black hole that's making some kind of noise on its own?
Yeah, that poor little thing's hard to detect. He's quiet. So there's a reason why the LIGO scientific collaboration and our counterparts in Europe and Japan are so big. It takes a lot of people. So there are a lot of people that have to do it just to understand that it wasn't an earthquake, that it wasn't there's so many noise sources that cause things to jiggle. So that's an amazing thing that happens. The people who understand the quantum shot noise of each photon hitting a mirror, you can go down there's so much stuff that happens. From my point of view, the reason why you have people like me working with detectors is not because they need my help on the detector, right? They do not want me anywhere near it. It's because we can theoretically predict what Einstein says is the equations say is the difference. So what happens is that astrophysically speaking, black holes are bigger. Neutron stars have a mass limit. We're fuzzy on exactly where that limit is, but we certainly can tell the difference between, I can tell you if we see the full signal, which means I see an in spiral, merger, and a ring down, and I see that full signal, we only can see that with current detectors when they're pretty massive. They're always binary black holes when we see that full signal, because black holes can be bigger. Mm-hmm. Neutron star binaries they're smaller masses, so their signal is weaker. And so we see them orbit each other for a long time, but we don't see them merge. Mm. So in a lot of ways, it's hard to distinguish neutron stars and black holes because in that in-spiral part, they look very similar. Mm-hmm. There are subtle differences because the neutron stars feel each other, so they get tidal effects that black holes don't really. Mm-hmm. But it is really hard. So we distinguish a lot based on the mass that we predict by comparing it to the theoretical predictions that people like me produce. Mm-hmm. So we use our understanding of the theory to figure out what all the physical parameters are. And then we use our understanding of astrophysics to say, those are the parameters of a neutron star versus a black hole. Okay. And then we start to deeply search for these other effects that could only be from neutron stars, like tides. But they're just a little bit harder in the data to see. But that's very exciting. And then we don't really know the equations of the matter inside neutron stars. So that impacts all this. So one of the big things we would like is to get enough frequency band to see the merger of the two neutron stars, because that would reveal what actually was the state of the matter inside the neutron star.
Yeah.
That would be cool.
That would be really cool.
Mm-hmm. That'd be one of the coolest things. But we're not there yet because our frequency cuts off before.
When you say state of the matter, do you mean kind of like solid, liquid, gas, plasma, or do you mean the actual density and elements?
The density, the pressure.
Okay.
Because there's no lab on Earth where you could reproduce what's in the neutron star, so it's a big unknown. Like the first binary neutron star merger was fun because people are like, oh, it made platinum, it made gold. Like we realized it could make all these elements, in part because we saw the electromagnetic counterpart to two neutron stars merging, which means telescopes that look for light also saw the same event we saw with the gravitational wave detector. So we learned a lot about it because we had all these ways of studying it. Mm-hmm. But it would be really great to so those neutron stars, when they merge, they disrupt all that incredibly dense material, and so we could learn a lot about it just from the gravitational waves by how it merges, because we can simulate a bunch of different choices for the matter, and so we would be able to some extent know, oh, it's this kind of thing inside there.
Mm-hmm. Okay. That does remind me a lot of my field, which is geophysics, mm-hmm. right? And what especially reminded me is when you talk about noise. So for polar geophysics, the even more niche thing that I research, you'll fly a plane over an ice sheet, and then you'll have a gravity meter on the plane, and to even so to calculate for your position in space, you have to have a supercomputer on the plane that corrects for all of that while you're flying this gravity meter, and then the actual deciphering what is a measurement and what is noise is like the single greatest challenge in using that kind of data. So I would imagine for it's even more precise gravity meters like LIGO,
we need 10 to the minus 21.
Yeah, which that is absolutely insane. Yeah.
It's crazy. Yeah, but it's fascinating, isn't it? Mm-hmm. Like what we can actually do if you have enough people working on it. It's like, wow, that's amazing that we can do that.
Yeah.
Pretty cool to be able to fly over detecting things too.
Mm-hmm. And then, so you talk about how neutron stars differ in their kind of, I forget what this.
The
orbital.
The tidal disruption.
The tidal disruption, like the different phases. There's the merging and the ring down, and then.
Everybody does that.
Okay.
They have what we call inspa, merger, ring down. All it means is I were two objects, I became one mushy object, now I'm a single object. That's what it means. Yeah. Both binary black holes and two neutron stars go through that same process, but LIGO's, the frequency that neutron stars merge is a little too high, and LIGO's not sensitive to it.
Okay.
Just because we know there is fundamental noise like shot noise, so we have to build a new detector to try to get at that frequency.
So what about black holes that have a lot of material around them? Do they experience, like are you able to pick up some kind of tidal frequency from black holes that are...
Not on the gravitational waves.
Okay.
Because you need a lot of mass to perturb a gravitation. That's a lot. It's very hard to, you can imagine, forget the black holes LIGO sees right now, because they're actually not that much. They're like a little bit bigger than the neutron star, up to about 200 times the mass of our sun. But those are relatively small black holes when you have, black holes at the center of the galaxy, which are 1 million to 1 billion times the mass of the sun. So the ones at the center of our galaxy, we would expect to be surrounded by matter if it's an active galaxy. And you can even imagine a binary black hole pair sitting there in that accretion disk. People look for those signals. It is more likely that you would see that from an electromagnetic disturbance than it would be from a gravitational wave. So when we look for electromagnetic counterparts, we call them, it's because something's happened, either binary neutron star where you expect there to be an electromagnetic counterpart if it's close enough to us, because there's a limit of what we can see, or black holes in some kind of rich, dense environment, then we would look for the light that's being disturbed because of the stuff. We have not seen that from black holes. It'd be cool. we expect with the space-based mission, LISA, which will fly somewhere around 2035-ish, we expect to be able to see electromagnetic counterparts to the big boy black holes, the million solar mass black holes merging.
So say that I take, so Andromeda, the Andromeda galaxy is getting closer to us as time goes by. So I fast forward. I'm not sure the exact time scale before our galaxies merge.
I don't know either. Anyway.
Some
very far away. Our
point in
sun's
the very
already
far
probably
away.
red gianted. Yeah.
Yeah. Some point in the very far away future, we're all disintegrated from the sun swallowing our planet up. Does the supermassive black hole at the center of Andromeda merge with our black hole?
So this is one of the big questions in astrophysics. And so that's why one of the reasons why people are excited about detectors like the space-based, because it would actually be able to measure those two black holes merging, and it will solve this question of whether or not when these galaxies collide, there's a lot of reasons to think that those black holes do find each other and do merge, but it's not definitive. So we need that evidence, and the gravitational wave would be definitive because we would know the masses, we would know that they did. So that's one of the big excitements about the space-based mission.
Yeah.
And would also see the single black holes that are big. I sang Beyonce in my head, the single ladies, for a second. Good thing I didn't do it out loud. So they would also, Lisa also can see like a small thing fall into a really massive black hole. So we could look for those. We can't see that with ground-based detectors. Yeah. So there's new fun things.
So how does, so if I have a black hole that's a lot larger than another, that larger one is going to swallow up the smaller one?
It could.
It could?
I mean, it doesn't, you can't disrupt a black hole. So the end state is always another black hole.
Okay.
Not quite the same mass as adding the two together, but close because we lost some mass to radiation. We converted some energy into radiation.
There you go.
Same thing as the angular momentum.
Yeah, that's...
Yeah.
Yeah.
So what's crazy about these mergers of these black holes is that the percent of energy that gets converted to gravitational waves is like 5%, which is huge energetically. Like it's more than the light we see shining. It's just that we were completely blind to it. So they're incredible producers. It's just that gravitational waves are hard to find. So.
And from what we've been talking about, it seems like gravitational waves decay as they travel through space.
Yeah.
Right. What causes them to decay?
It's the same as light. So there is the same style of, as you propagate, you lose like factors of 1/r as you get further and further away. The difference between light and gravitational waves is that when you look at the Milky Way galaxy, if you go to Big Bend or somewhere where you can actually see it, you see those dark bands that we call dust. So there's things between the center of our galaxy with all the stars there and us that absorbs the photons. Otherwise, the sky would be, be really bright, right? Gravitational waves don't interact with things so easily, and so we get it from much further away. We can really see it. We can see that we should see pretty far back in time with gravitational waves in a way we can't with light.
How far back in time do you think?
With the new detectors, the space-based detectors, they say Z20. So really far back. Like we'll see all the black holes that are merging.
And oh wow, all of them.
Yeah. Between the next generation ground-based that see the lower mass and the space-based see the big boys. And we also have the pulsar timing array, which sees 10 to the 9th solar mass black hole. Oh, that means 1 billion times the mass of the sun. We'll just see everything.
1 billion times the mass of the sun. That
it's crazy.
You can't even comprehend
no.
it. Yeah.
Yeah. To me, it's just that becomes a little number. I mean, what are you going to do? It's like the deficit is smaller than the deficit. That's not so bad.
So is measuring gravitational waves or trying to, I guess, invert the function of how quickly they decay from the data that we observe? Can you get an age for like how old are these waves that we observed?
You can say, oh, I used to know this so well, and now I don't. The first detection, we would say it was from 1.5 billion years ago. Because you know that if we suspect, we haven't proven yet, but we suspect that the radiation travels at the speed of light. The theory predicts that. And the detection measurement gets a sense of distance. So yeah, we do know how far away they were. We have a good measure of how far. We don't see neutron stars as far away because they're not as massive. So that's why we see more binary black hole events than we do neutron stars, because we can see a larger volume of space for the black holes.
How do you differentiate between how far away are these and then in space, and how far away are these in time?
That we don't. That's like equivalent.
Oh, okay. Because you're assuming that they travel at the speed of light. Yeah.
So for me, the units are the same. Like I would say it's equal to 1, and the units of mass and time, or length and time, are the same. It's convenient. Yeah, so we don't bother with that.
Can you pinpoint like an origin in space?
That's hard.
Yeah.
So just with our LIGO detectors, there are 2 in the United States. If both of them see the event, we get like a huge banana-shaped thing. And there's so much in that shape that you can't even point a telescope. If the European detector Virgo's on, you get a bit better. That's why we want more detectors around the Earth, because then you get a better and better localization. So we did see one event, binary neutron star, with gravitational waves and electromagnetic. And that one was everybody's like so excited. And they're desperate for another. But so far, all the detectors, we haven't gotten lucky. The source hasn't been close enough, and we haven't had everybody on and seeing it at the same time. So we get really poor localization evidence.
Okay. And then how does a gravity wave interact with gravitational wave interact with local distortions of space-time, like gravity on Earth, right?
Yeah, I mean, it almost everything you can imagine that is like electromagnetic radiation kind of happens with gravitation. So have you heard of lensing?
Yes.
Like the Einstein cross or the ring. So if you have in astronomy, if they're looking for light, sometimes they see interesting patterns of light because there is what they call a lens, or some massive object in between us and whatever was producing the light, and it distorts the light. And so you see weird patterns.
That's how we've inferred the location of some black holes, right?
Right, exactly. Yeah. You do things like that. In principle, gravitational waves can be lensed by big objects. It's just such a small effect that we can't detect it yet. Mm-hmm. So a lot of the things that you learned about electromagnetic radiation will hold true, but it's always like it's often at this really reduced thing. So we haven't seen any of that.
Mm-hmm. And then thinking like kind of cycling back to the propagation of gravitational waves, when I hit this table, a wave travels out towards you, and the reason there's a wave is because the atoms on my hand hit the atoms on the table, which hits more atoms, and it slowly travels and propagates through. But how does like a point in space-time, does the contraction of one point initiate the dilation of another?
How do photons travel? Can photons travel through a vacuum?
Yeah.
Yeah, but they're not. What are they jiggling?
Exactly, yeah.
Yeah, so it's the same as a photon.
Okay.
In that sense. You know, it doesn't, like the kind of wave you're describing makes a lot of sense for a geoscientist to know about.
Yeah, I'm kind
of
biased with this stuff,
It makes so much sense. And I know less about that world. So you don't actually, the problem with the gravitational wave is that the way you learn about electromagnetic radiation, there's this dual personality. It's a wave, which you learn in basic class. You learn the perturbation. I mean, you learn the knocking into each other, like you were describing a wave on the table. But photons travel through vacuum, so they don't have to vibrate their neighbor to make it. I wish I had a better way of describing these things. Anyway, but the problem with gravitational radiation is that we don't have this dual nature of a photon and electromagnetic wave. We'll call it a graviton, but we don't have a theory that predicts a graviton's existence. We're just implying it has to be there because we assume there is some quantum nature to general relativity, and we just haven't unveiled it. Mm-hmm. And it's the graviton that travels at the speed of light and manifests as a wave, but all of that is not proven.
Gotcha. So there's where does your field go in the next
Yeah, so there's
years,
lots of things. There's people who do string theory and loop quantum gravity that are trying to figure it out, and I was kind of hoping there'll be some smoking gun evidence somewhere in a gravitational wave because it's brand new, and usually when you open a new window into the universe, as we like to say. Mm-hmm. But so far nothing It's all been consistent so far.
Yeah. And thinking about space and time as the same thing, because my original question that I have written down is like, how do you account for such heavy time dilation at the at the origin of the wave that you observe? But since you can kind of treat space and time as the same thing, since what you're perturbating is space-time, right?
I'm not sure if I understood. I mean, time dilation is also an effect of when you're making comparisons, right? Mm-hmm. So the wave has its proper time, it's propagating. Mm-hmm. It's like if you want to compare two things, then you'll get trapped in the time dilation trap. The clocks will run at different rates, but I don't understand in terms of the wave.
So like, I mean, again, I'm thinking about it in terms of geophysics, but like if I hit this table and a wave travels out, time here, because I'm close to this black hole, is different from the way time passes here. And so if I'm trying to observe how does this wave travel through space and time.
Yeah, we only see it here.
Okay.
Right, so we are detecting it here, which is basically almost equivalent of flat space, right, outside the Earth or on the Earth. It's not really curving anything. So actually the gravitational waves that the Earth sees, you could treat like just a little perturbation on flat space-time.
Okay.
When we do our calculation, our full calculation of the two black holes, that's different, right? You're right. Time is funky there. But what we do is we extrapolate what the wave looks like at Earth. So we sort of separate the problem. We just predict what it's going to look like when it arrives to Earth.
Okay. So you don't really even try to make the comparison between. Okay.
We do things. So a lot of those time dilation, all that kind of stuff, it also is mired in coordinates, right? There's a coordinate clock. There's your clock that's proper. So we try to always do things in some coordinate independent way, some truly physical calculation we can make so it's consistent. And that's what gravitational radiation is an example of that, so that we can be relatively coordinate free when we produce it.
Okay. Yeah, that makes sense. And then as far as the origins of the universe and gravitational waves are concerned, is there a field of research on gravitational waves trying to find like kind of noise from way back at the beginning?
There's in some of the cosmological experiments, they look for you would look for like a gravitational wave impact on the fields that they're measuring. So yeah, people do this for sure. It's hard, but people are doing it. Mm-hmm. A lot of it is like looking for stochastic backgrounds, so like almost like a hum.
Yeah.
Just like there was a temperature that they discovered of the universe. So you'd be looking for like the signal summing up from the very, very early universe. Okay. And looking for that evidence.
Yeah.
People do that a lot. Mm-hmm.
Okay. And then also another big concept in physics that I've been exposed to is the Hawking radiation, right? Have you observed any effect of that phenomena on what you study with black holes?
No, wouldn't it be cool?
That would be
So
cool.
the problem is that these black holes are astrophysical black holes. They're big babies. Their Hawking radiation is not detectable. You could do a toy experiment and say, depending on a lot of choices in the theoretical landscape we'll ignore, could you form a little baby black hole in CERN from particles colliding? And it'd be so tiny it would evaporate instantly, and could you measure the particles that were evaporated? Or were there primordial black holes formed in the beginning of the universe that would be light, like 10 to the 14 grams? And then would they be evaporating now, and could you see that? But there hasn't been any evidence, and I don't even know how you would look for that, right? Because, these black holes are too big. Mm-hmm. Their evaporation is, like, longer than the time of the universe. So, it's not a realistic effect for us to be looking at right now.
Okay. Yeah. Theoretically, would the time of evaporation be small enough to where if something formed at the beginning of the universe and now produces a signal now that travels through space and then whenever it gets to us, we're able to observe it. It would
wouldn't
be less than.
It wouldn't be gravitational radiation is the problem. It would be some kind of electromagnetic radiation we'd look for.
Okay, so maybe I'm not fully understanding Hawking radiation.
Oh, well, me either.
Yeah.
Forget about it.
Do they lose mass through time, or?
Yeah.
Okay.
I mean, but this is a semi-classical. This is pushing our understanding of the theory pretty hard. And that's great. You have to. Because you found evidence for it, you would know. Okay. So the idea would be that literally the black hole evaporates, so slowly its mass would go to zero. And you would get this radiation out that would be a signature of that's happening. GR, that doesn't happen, right? It's there forever. It doesn't move. So you bring in these semi-classical things that Hawking did to find it. But what I don't know, I do know that if they were small enough, like I don't know why 10 to the 14 grams, but I guess that's to see it evaporate in current day if it had been born in the beginning of the universe. That would be the size of the mass of the black hole that would be evaporating now. Mm-hmm. But I don't know how you would detect the radiation or how far away you could be from it and detect the radiation. I don't know any of those things, sadly.
I have no idea.
Someone knows. It is not me. I don't know. They're fun questions.
Yeah.
I don't know the answers to all of them.
Yeah, so you're like taking, I guess in a black hole, you're swallowing energy and mass that theoretically is never going to be able to go back into the universe, but then Hawking radiation says that some of that energy and mass
it's
is
one
able
of the
to-
big conundrums, right? Like,
Yeah.
do you lose entropy because of the black hole? And there's an amazingly interesting amount of science being done there where the people think, no, right, it's not lost to the horizon. Somehow the state is encoded on the horizon, or there's a firewall. There's all these other things. Could we get to the point where we could see that in gravitational waves because we can start understanding black holes well enough? Maybe we'll eventually be able to tell that. I don't know if we're going to actually be able to, on Earth, measure the radiation from an evaporating black hole. Yep. I just don't know how close you have to be and what its signature would look like. And I don't know if anyone knows what that would be. Probably the one in a particle collider was more realistic. Okay. Because you have such sensitive, but they haven't made any black holes. I mean, I think we would have heard.
Yeah. So, oh man, you could theoretically smash two particles together.
You have to make a lot of decisions about things.
Yeah.
Matter and blah, blah, blah. But yeah, you can imagine it happening.
But that black hole is going to fuse
Evaporate
out
instantly
because it's so small.
Mm-hmm.
Gotcha. It's like the size of a particle.
Exactly, itty bitty. So it would just boop. But I don't know enough about it. Like, that's sort of my extent. It's like a cab ride knowledge that I have about that.
That would be crazy if we created a black hole and then instead of diffusing really quickly, it swallows another particle.
Yeah, there was
another one and another one.
You never saw the
one.
YouTube video? There's a YouTube video of CERN getting eaten by a black hole that it creates, and it just slowly eats the Earth. It's very fun.
No, I haven't seen that.
Yeah, it's a good one.
That's a good one to
It's a
watch.
really good
I'll
one.
link it in the show note captions.
Watch it disappear. It's very fun. People were worried for a second. I don't remember what must have come out, but I remember literally taking Uber rides or cab rides where people would be worried, and I would have to try to be like, it's not going to happen.
Yeah.
But you can't help.
That reminds me of it's going to be a total tangent, but a colleague and professor of mine who studies ice sheets was talking to an Uber driver of his who just came out as a flat earther to him.
Oh, yeah, it's happened to me too.
Yeah. And he tells him, like, I've been to the Arctic and the Antarctic, right? And he's like, did you see the wall?
I love it.
What did it look like?
Yeah, I got picked up outside of NASA.
Mm-hmm.
And the guy was like, asked what we were doing at NASA. And he's like, I'm a flat earther, so I know you weren't doing anything. I'm like, why are you even talking to us then? What am I going to tell you? It's very fun.
Yeah, I wonder, that would be, depending on the type of person you are, picking people up from NASA in an Uber and then also having a strong flat earther stance would be a engaging job,
fun.
to say the least. It could be fun. Yeah.
It just depends. A lot of times there's a real deep-seated something that if you touch it, it's not a nice thing, right?
Yeah.
There's We had a local gravity conference recently, and there's people who've been working on a theory. The problem with physics at some level is that the mathematics you need to truly understand what's happening, like I don't have it all, so I can't sit down and do string theory because I didn't study that math. So there's so much of it that people who didn't have it all try to speculate, and it just goes badly, right? They come up with their own theories that I was joking that I was creating a crackpot in our oldest son because I wouldn't have enough math to explain to him fully, and we get to a point where I was starting to be like, oh God, now you're going to believe this, and it's not quite right. Mm-hmm. So it's tough.
Yeah. There's a very, for one thing, I would say a majority of scientists care more about just solving the problem that they enjoy to solve and less so about telling the whole world how cool their problem is. There are plenty of people who love sharing their problems with the world, but
it's hard.
Yeah, and it is hard to communicate these really, really technical ideas with people because it's hard for you to fully understand it. And you don't have all the answers, and you're still trying to figure out. And it's just like how you were saying earlier, like you would have to resort to all of this really technical, I don't want to say jargon, but...
You can say jargon, it's true, right?
Yeah.
We invented that language to make, so we can talk to each other. It's bad because we're also afraid to say something wrong on film, right? And if someone sees it and thinks I'm an idiot, one of my colleagues that I care about their opinion, right? Because I will make mistakes. It's inevitable.
Yeah.
So there's also that reticence to speak to the public in fear that you will say something wrong. Yeah. And we don't have the language.
And there's such a... I don't know, academia can have a lot of drama, and I don't want to say this on the internet because then someone else will see it and it'll get back to me, and then it'll, disrupt this research I'm doing, and you have this careful balance of like people and workplace relationships and stuff
it's
like
even,
that.
A few times, because it was a really big deal when the first gravitational wave detection came out, and I used to be at a different university, and they were doing a lot of press. And just the amount of people who hate you because anything happened is I'm not necessarily someone who wanted to be in the public sphere, so I'm not going to do things necessarily to put myself there because it's like, what? Okay. People love to do that. So.
What happened exactly?
Oh, it was just that there was all this publicity about the event and the trolls, which I didn't read them all, but they'd be like, okay. Oh, because you're a woman, this is all fake, you don't know anything.
Oh, okay.
This guy's silly, right?
Yeah.
Because there's always that. And, I don't really care, but I can imagine it being annoying for people who really step out. Like, there are the people, scientists, who have a public presence, and they give public talks more than what a normal scientist like I would do. Or they write public books, and they go on these late-night shows, right? So.
Like Neil deGrasse Tyson. That's a good example from your field.
He was at UT for a little while.
Yeah.
Yep, like that.
Did he got his master's here?
He probably left with his master's and went to Columbia.
Columbia. But he's a great example because he's done so much good in he's such a good communicator, and he's really good at explaining physics to people that aren't super familiar with all the technical jargon and stuff. He has a book, I forget the exact title, but it's basically like Astrophysics for Dummies.
Yeah.
And but his entire personal life and all of his mistakes throughout his life have been publicized to the entire world because of that. So it's...
And scientists are a bit like, well, what science do you do? Right? Because he's such a public persona now. Yeah. And then you have others that sort of maybe are still doing really deep science work at the same time as every now and then writing a book and having that. So it's complicated.
Yeah, there's definitely a component of, like the more you put yourself in the public eye and the more you focus on like sharing your problems that you're trying to solve with the world, the less time you spend actually trying to solve the problem.
Yeah.
So you're like... So the actual research that you want to do kind of stagnates, but the amount of people that know about what you want to do
I think some
increases.
people like that. Like, you must make a decision. Well, we did a lot of stuff for LIGO that would show up on the front page of like BBC, New York Times, because we visualized the gravitational waves coming out. And it'd be a really popular movie. But that was with the level of our of our engagement. You could hide behind the LIGO collaboration. But that was fun engagement because it was like, oh, this is so cool. The front page, people would be excited for a bit, and then it would die away and it'd be okay. Not too much. So that was fun.
I'm curious how it seems like black holes have gotten more popular in recent years, especially with movies like Interstellar and then the huge breakthrough of LIGO in 2015. Have you noticed like your field kind of becoming a bit more popular as the years go by?
There's two things. So people have always been obsessed with black holes. That the public always been true. Even like I visited Congress a couple times, and I would start talking about gravitational waves, and one of my colleagues was like, "Just stick with the black holes. They don't know what you're talking about. If you know, just stick with the black holes." Because there was just such a love of them, right? Fascination with it. But we also have, because of the success of the science, way more people want to go to grad school in it. So there's both impacts. I think also like the event horizon, there's been more and more evidence about black holes that's fun, like the Event Horizon Telescope, LIGO.
And there's the picture of like the first picture of one.
I call it a picture of a parent horizon because I'm a pain in the butt. And then there's like the pulsar timing array that's been gathering evidence of a hum of gravity. So it's coming from everywhere. So it's a really cool time.
Yeah, personally, I've seen just so many huge developments. I think the first picture was the biggest development, or like the most viral development
it was the most easily accessible.
Mm-hmm. Yeah, I guess it's hard to, because you like for LIGO,
we don't
now you have to like try to understand what is a gravitational wave,
right? But and what you're not, I mean, you are kind of seeing a picture. You're seeing computer realizations of what the thing would look like.
I will say that the little animations of swirling and then merging and then
those are what
the ring down, those are great.
Yeah, because we can
like
see
those.
it, right? It's not light, but we can help you see it. Yeah, we know it's okay. It's part of the game. But it's really exciting to have been a person who worked on it. No one thought they would be detected, and getting to be part of the experiment when we saw them that day, the first day of first detection, it was just like,
I bet that's
what?
surreal.
Amazing. Yeah. It's crazy.
I mean, we talked about how how LIGO was important for Einstein's equations and his prediction of a black hole, and I would like to revisit that a little bit and just ask you, like, why was the first detection of gravitational waves in 2015 such a huge breakthrough?
So there, in the 1990s, there was a experiment that saw in pulsars, which are these really fast, rapidly spinning neutron stars that almost act like a clock because they're very stable in their rotation. And they were in a binary pair, so we love binaries because we can see the evolution. And so they watched, this was Hulse and Taylor, it's called the Hulse-Taylor pulsar, and they saw the orbit decay in a way that was predicted by the emission of gravitational waves. So that was the first test of general relativity outside of like sort of simpler solar system tests, like the Mercury's precession of its perihelion and things like that. So that got a Nobel Prize maybe in the 70s. I don't remember. Yeah, 70s. It was in the 70s. I was not paying attention back then. But that was indirect. That was like, what could be causing this orbit? It agreed beautifully with a gravitational wave prediction, but it was not the detection of a gravitational wave. So the reason why the LIGO experiment got a Nobel Prize from detecting this is that was the first definitive, you've actually measured something that for the first time ever, it'd be like measuring light for the very first time or sound for the very first time. You know, there's no way else to get it, this information. We had no idea that two black holes, I mean, astronomers said the event rate of two black holes being together in a merger was 0 to whatever because you couldn't see them any other way. So not only was it the first detection of a gravitational wave, it was the first detection of two black holes merging. You know, so it's a double whammy. Yeah. And, you know, that was the first definitive, that was the most definitive evidence, right, that the prediction was correct and they exist and the black holes do too. Because it can't be anything else. Like when you maybe they could be quark stars, maybe they could be weird boson stars. But when you look at other things, like how else do we know about black holes? It was from gas and matter interacting with the black holes, so it's not as definitive as gravitational radiation gives you, because there we have the direct prediction from Einstein's equations of how it should behave, instead of sort of inferring the properties. Gotcha. So if that helps, there you go.
Yeah. It's like what's a good geophysics example? It's like the difference between inferring all these properties within the Earth from seismic waves and different phenomena, and then actually being able to drill down there and like see it for yourself.
Yes.
Yeah.
It's a big difference. Mm-hmm. And a lot of the stuff that electromagnetic radiation gives us is external. Like, you know, when we saw those two neutron stars merge, we knew it was two neutron stars because we can compare it to the theory of prediction. Where the people who studied these gamma ray bursts never really knew if it was a neutron star binary that was causing it. Mm-hmm. So it allows us to jump in our understanding of things because we peer deep inside these stuff.
Yeah. You're able to like just put your hands on the phenomena itself. Kind of. Yeah.
Don't recommend it, but yeah. Sorry.
Hands will stretch. And maybe you wouldn't notice it. Maybe you would.
I think one of my PhD questions was what happened if you stick your hand in it. But anyway.
Really?
I think so. It's a long time ago, so I could be making it up at this point.
Yeah. I did not. I read your thesis, actually.
That's why you asked about Apparent Horizons. I was wondering.
Yeah. And I didn't see it in there. Maybe I need to.
Oh, no. It was in the oral exam.
Oh, okay.
Yeah, we get asked questions.
Oh, they asked you that question?
Yes.
Whoa.
Yeah, I think one of them did. I got my PhD here, right? He passed away, Larry Shepley. I feel like he was asleep and he woke up to ask me that. I was like, what? Okay. It was very fun.
That is a fun question. Were you like nervous and then you're like, what?
Because in retrospect, it's reasonable to ask me that because my work was so about apparent and event horizons. Mm-hmm. So it wasn't a crazy question when you think back on it. Mm-hmm. At the time, I was probably freaked out.
So how much of Einstein's theory of relativity holds up with what we've observed so far? Does it all hold up? Are there things that are a little bit shaky right now?
It's all consistent. At some sense, you want to be disappointed. You won't believe the amount of time we spend trying to test here. But it's also such a baby field that I think we all have to calm down. It's been very consistent. Of course, it is a very successful theory. We don't even know if gravitational waves is going to be a way to really probe it. You know, we got to try, but it all has been consistent so far. Mm-hmm. But we're 6 years in, 8 years in?
Yeah.
So.
Yeah, give it another 2 decades, 3
give
decades.
It some time.
Yeah.
It's wonderful that it's as successful as it is. I love all the black holes it's seeing. It's really fun. We didn't know the black holes could be that massive, so we've learned a lot, but we just have to be patient.
I was surprised by how easily, because quoting Einstein, one of his biggest blunders was assuming that the universe is not expanding, right? Mm-hmm. But in order to account for that, all he did was just change the cosmological constant, right? Mm-hmm. That's all he had to do.
Mm-hmm. But we don't understand that still. It's such a simple modification. Mm-hmm. We don't know what dark energy is. Yeah. Is it because we don't understand gravity well enough? Or is there some field unaccounted for from the beginning? We don't know. Yeah. There's a lot we don't know, which is exciting. It's just that when you're a scientist, you gotta, you get very specialized, obviously. And then you have to kind of pick your battles, right? So I'm focused on the gravitational wave battle, but I'm very interested in what, the cosmologists find and things like that.
Yeah.
Yes, sir.
A question that I forgot to ask.
Okay.
So let's loop back to the propagation of gravitational waves.
Oh, yeah, you said something. Yeah.
How does the expansion of space-time interact with the propagation?
So one of our problems is that the distance and the mass can get confused because, it's expanding. Mm-hmm. So something could be of a lower mass and closer than we think, or a bigger mass and further away, and that does get confused because of the expansion, that we don't necessarily have a clean we call it luminosity distance, that you can get fooled.
Okay.
Because they'll look the same.
Yeah.
So that's a problem. Yeah. So that's how it happens. It confuses us in terms of mass.
And in terms of mass of the object.
Like the total mass. If it's two things forming, we tend to talk about in terms of the total mass of the first two black holes before it merges. That's how we talk about it.
Okay. So you would just like say in your model, this is how fast the universe is expanding, and then
it's a simple.
You would just add the.
It's like a 1 plus z. It's really simple. Okay. The calculation's easy. So it's just it scales with how far away it would be. We also get a measurement of amplitude and frequency, so we can figure things out to some extent. It would be very definitive if you have a electromagnetic, like if you can localize the thing and say it's in that galaxy. So then we would really know. We can disentangle it. Yeah. It's just something that happens so that you can misunderstand things when in their what mass you think they are.
And how does the expansion of space-time differ when you're, say, close to a black hole and now you're like really distorting everything? Does it differ?
No. I mean, that's sort of just a different scale. Okay. There's the expansion of the universe, and then this binary black hole is living inside that expansion the same way we are. But there's not really something I would say is different in that vicinity.
Okay. And it's homogeneous across everything we've observed so far?
So as far as we know.
Wow. That's really cool.
It's really cool.
Yeah.
But, that's something that I'm as curious as you are, and maybe only slightly more knowledgeable, right? There's so much out there. I mean, we have a cosmology center. I listen to them. But just like my language will get too jargoned, eventually I won't really understand without studying it, without taking the time.
That's why I really, really like another complete tangent, but I really, really like AI and ChatGPT because you can ask it these questions and then it'll just explain everything to you. Yeah. And you can just be at it for hours and it'll, like, I could probably plug in, I would not get as accurate of answers, right, of course.
But you would get something.
But I would get something that would get me kind of on the right track. And then read some papers, give it the text in the paper, and have it give you like little bullet points of.
We have to. I think professors have to learn to use it effectively for the students.
Yeah, it's such a weird. Because now, like, the entire bar for everything has just been raised because, like, lazy writing back in the day used to be. I'm writing something down for 15 minutes and I kind of slap it together and then I give it to you. Now lazy writing is I ask ChatGPT to do it for me, right? So now the bar is raised to the level of the AI that you're using. So now you have to spend like the same amount of time you would, but just differently.
Yeah, and we have to say, how do we incorporate that to use it wisely? One of the problems we have, like some things I don't care about. I remember when people worried about, in my day, like cursive writing was going to disappear. Who cares? We don't need it, right? I mean, who cares that you don't know how to dial a phone because you've never seen one? I don't care about that stuff. One of the things we worry about, though, is that if you use machine learning for everything and you no longer know how to solve a partial differential equation, like machine learning isn't always applicable to every problem. It's sometimes you know the answer, and that's better to know the answer than to collect a bunch of data and let the machine learning algorithm.
Yeah.
So I guess we have, and that ChatGPT doesn't necessarily, it has a boundary there somewhere too that I don't know where it is. So it's hard for us now to figure out, like, what's the level? Like, it's so much to learn. Mm-hmm. And if you don't need it, if you just do it with ML or do it, I don't know, it's very hard.
Yeah. There's a level of, like, I talked about this with my first guest and he gave a great quote on kind of ChatGPT and AI. It's super competent, but there's not a lot of comprehension. Mm-hmm. So like thinking creatively about these big ideas, like AI could never replicate what Einstein or Hawking or any of you guys on LIGO, like the creative thinking that went into observing these things and like the creative thinking of trying this theory out. Oh, it doesn't work. Okay, let me like try this one out, and then creatively trying to like reorganize things in your head. It just takes what we have built through our creativeness, and it's really competent at recreating that. Mm-hmm. But yeah, developing new things is something that it is not so good at.
Yeah, it's interesting.
Yeah. because it's kind of on that border between human and robot.
It's also at the mercy of the information you've fed it.
Yeah, exactly. And if you give it all the information in the world, then you run into problems of like there's a lot of really bad stuff on the internet, and it'll make bad stuff.
Right.
I think that happened with Google recently.
Yeah, something happened. And it's like people believe everything they read here. It's like, well, no, and how do we know it's wrong? Like, why am I able to do that and say, I know this is not, and my father no longer can? Like, I don't, that's interesting too to me, how we can look at similar things and I'll be like, fake news.
So I apologize for going on such a tangent outside of black holes.
My knowledge.
Coming back to, but keeping on the topic of AI, has there been an attempt to try and implement AI into these huge, like, differential equation modeling and stuff like that you guys have done?
Yeah, it's hard, but yeah, like I tried almost once to collaborate with someone who we were going to try to do that, but we never did it. It's complicated, but yes, people do, not at the level of Einstein's equations. Those are the hardest kind of the hard. But yeah, there has been work on how to, at the level of how we do differencing, take a derivative, do that with some kind of AI algorithm. It's been more impactful in dealing with noisy data and managing large data sets and getting new answers that way. That's probably its most applicable in astronomy and like particle physics and gravitational, is that people use the AI to do that. Just look through all the data and try to find new things, or figure out that was a noise, classify noises and things like that. There's been less work on the PDE level. People do it, and I think people do it here too, in the Odin Institute. Yeah. But it's something I wish that I had the bandwidth to do. I think I would need a special student who was excited about that. Yeah. It's tricky.
Advertisement for potential
by the way,
Shoemaker graduate student.
It would be a really cool thing if someone could. I mean, I'm afraid with those stuff because I don't know its limits, and so I have to have a colleague who does. It has to be a collaboration, so we don't do something stupid. Waste that grad student's time.
Mm-hmm.
That is what I'm afraid of. But it's cool stuff. Done?
I am all out of questions.
Yeah, you told me it would take longer than an hour. You were right. I'm like, oh my God, but you did a lot of research for this.
I did.
You have to, because I was like, what is he asking now? Oh my God. Yeah. That's got to be a lot of time. How many hours do you spend preparing? It's a lot.
I don't know. I spent a lot of time reading papers, and so usually my workflow for preparing for a guest is just like opening up every website and then every talk they've done, and like every I like to go to the talks first, because that's like probably going to be the stuff that you want to talk about, is the stuff that you're like going to a talk to do. So that's what you're going to want to talk about on a podcast, and then just to understand like the nitty gritty of the research, maybe not even understand it, but get an intuition of it, so I can kind of place my brain in a like a gravitational waves mode, where I can kind of create questions in my mind.
To notice neutron stars versus binary black holes. To know to ask about that. Yeah, that's hard.
I used a lot of ChatGPT for this, just kind of like I didn't ask it to print me a bunch of questions, but I was like, okay, what is Einstein's field equation? What are these different constants? What do they represent? How does this interact with this? And then you kind of fact check everything by going to papers.
Like the Cliff Notes. Mm-hmm. I think it can be really useful by doing what you just said, by fact checking, like having a sense, and it allows you to quickly synthesize all that information, and then you can kind of go in and look. I guess it's only if we start shortcutting checking, we're in trouble.
Well, yeah, that's exactly. Well, I made the mistake of thinking it was infallible when last year, when I was doing my own research, and I tried to use it to give me equations and like basically give me the answer to my problem instead of helping me with my problem. So I'd be like, hey, give me an equation for this phenomena. And it would give me an equation. I'd be like, okay, give me a source for this. Because I want to fact check obviously. It. And it gives you a source, and then you look up the source and it doesn't exist. Yeah, it'll just completely lie to you. So you really have to be careful about.
That's fascinating.
Yeah. Because it's going to give you an answer. It's just that it's not always going to give you the right answer.
Right. But if it's if it's always going to give you something, then it's going to be wrong. Okay,
Yeah.
that's really interesting.
Especially when you really get technical with it, and research is all about doing things that people have never done before.
Yeah, it's dangerous land.
Yeah, so when you're really getting technical about things that no one else is thinking about. So in my example, it's like some subglacial environment on some Canadian island that maybe like there's a local population of like 40 people, and then maybe 40 researchers have ever been there.
Wow.
Wow. Probably more than that, but
it's something niche. It's
yeah,
tiny.
It's super niche.
Wow.
It doesn't really know that much. It has the intuition of like the stuff that it's read, of the information that it's given, but you really have to be good about fact checking.
I do think that me and my students are underutilizing it for what I just don't remember. Like after 20 some years in the business, I have papers that I no longer remember that I wrote, let alone my colleagues' papers. And so I have a student who's asked me a question right now, and as you spoke, I was like, I should probably just ask ChatGPT. And I never do. I've never used it. But it's not that hard, right? I should just go do it and see what it says. And then I can check it and just remind me, oh, yeah, that happened. Because it's hard to remember everything.
Yeah, it's definitely, I think it's just a standard bar raiser. But if you want to, just like back in the day, if you wanted your research to be excellent, or you wanted, to ask excellent questions or to do whatever, you had to spend time with it, right? So you couldn't just meet the bar. And so now that bar is higher because we've implemented this tool. It's like Google. It's exactly like Google.
Yeah, it is just like Google. I remember my students, like, how come they look at my electromagnetism questions, like, well, that looks easier. I'm like, yeah, we couldn't Google the answer. Like you guys now, the bar had to go, so maybe we needed ChatGPT because the information is just too overwhelming to even parse it.
Yeah, but we've just moved the standard Gaussian distribution this way, right? But we haven't done anything to the actual distribution itself.
That's why I want to get better at using it, because I feel like it's almost as if I'm not Googling when I could, which is dumb.
Yeah.
You're just letting information go that you could get to.
It's so easy to use. You just got to ask it good questions, and then.
I'm sure it's very knowledgeable about precession effects and gravitational radiation.
Oh, yeah.
But it could be. Could have read all those papers. Not read, but no.
Here's a question. So I talked to a planetary geophysicist, and he explained to me the formation of the moon, and how there's this thing called evection resonance, which is the exchange of angular momentum between the Earth-Moon system and the sun as it's forming. And what that did is it allowed the physics of the entire problem to be compatible with the geochemistry that we observe on the moon and on the Earth, and kind of how everything settled and things like that. So I'm curious if you guys look into something similar when you're trying to model neutron stars, like an exchange of angular momentum between the two.
It's more done when people are talking about stars and white dwarfs and things that really form and accrete on each other. There's a little bit of neutron stars, but less, and nothing with black holes because it just eats it all. Like it's not but we do a lot of tidal effects that, like, how does a black hole rip a star apart? There are some things in planetary science that are resonances that people use similar concepts in our world. So there is a crossover of knowledge that way. It's not always one-to-one, but there is angular momentum transfer. There is the matter falling onto stars. So all that stuff does carry over to some sense. Just not the geoscience part, probably, because it's a different kind of compactness of the objects that changes things. But it'll be in some, there are threads that are very similar.
Yeah.
I don't focus on them because it matters icky, and I prefer my pure beauty of a black hole with no mess.
Watch, we're gonna discover something about dark energy that's gonna make it messy, and you're gonna have to find something else.
That'd be really cool. I won't complain if people discover something exciting. So thank you for your Friday afternoon.
Yeah, thank you. What I like to do at the very, very end is
sing. Just kidding. I cannot sing, so don't say sing.
Give you a moment to promote anything that you want to promote, or share anything that you want to share. Just give you the spotlight to where can people find you if they want to ask questions, etc.
Afraid? No. Very good.
Don't find me. Yeah.
Never look for me. I'm a physicist for a reason. I think that, I forgot now because I was laughing too much. Do I think there's anything to promote? Well, LIGO's going to start up again, so there's going to be fun things coming out. But that's not very exciting for the public. The public, I don't know. I didn't think about it before I came, so I'm stumped.
That's fine. Yeah.
There's outreach programs like the Particle and Pint. I don't run them, but they're at Darwin's Pub on 6th Street, and the grad students, undergrads, faculty, we all give talks down there and just hang out. It's fun. They're not doing a good job of advertising it right now, you know, but there's things like that that are cool. That it gives venues where you can talk, and then, you know, I don't like getting all the emails, and sometimes I get postcards from people who have their own theories of things, and it's just so much time to parse and read all that I don't have. So I feel bad, but like I don't want everyone's theory to send to me.
Okay.
So
Public PSA.
Remember the first time I got like a full binder and a video for some guy who had his own theory, and it's like I'm barely getting my own work done, let alone go look and see what math error you made somewhere else. So that part. But I love talking to students, as you know. Yeah. But even the little ones, they're fun. Those are the kind of outreach events I like. I like public outreach. But I don't have anything planned.
So if like a high school student was to be like, hey,
Yeah.
can I ask you some questions?
Yeah,
about,
like I don't want them in my lab doing research because I've done it before, and it's too hard on the students, my students who take the burden. But I love, like, I'll have one-off conversations, no problem. Or let's talk about that book that Kip Thorne wrote, whatever. But embedding people in my research, I don't start until they're in undergrad. Gotcha. Just because it's just a lot to ask my team.
Yeah, it's a lot to try to wrap your head around this stuff. Like in high school, I don't know if I could really understand it as well as I do now, and I still don't understand it that well.
And the problem is that we don't even talk about the cool stuff, right? You know, they're probably writing a Python script, which is sad but true. You very rarely step back and say, oh, why was this so interesting in the first place?
Exactly, yeah.
That's the sad truth of it.
Well,
anyway.
somber note to end on.
That's my way.
Okay, so bittersweet because what we're talking about is really cool.
It is really cool. It's really fun.
Okay.
Just busy.
Awesome. Well, thank you so much.
Take care.
Yeah.